Okay, welcome everybody. Welcome back and welcome to day 2 of our Urban Futures workshop. We have another terrific day ahead of us and a fantastic set of talks for the next session. Um, I have just one or two orders of business and then we're going to get right to it. One thing is I wanted to just call out what's on the slide there in front of you. I ran a little over in my talk yesterday and was just about to show my final slide, which was this one. And I did want to make sure just to get it out there, mainly because there are some links there that may be of interest to folks. I can also drop those into the chat. Kristen had mentioned some of these, but there are some big initiatives that Microsoft has launched that may be relevant and useful to us, particularly from a granting standpoint. So two of the big ones are the AI for Earth program, and probably the big one is Microsoft's Carbon Negative by 2030 initiative, which comes with a $1 billion fund for climate-related research, and also a whole bunch of tooling that's going to be going with that. I mentioned here on the slide this carbon calculator, which could be something that fits with what Tom was talking about yesterday, which is like tools for assessing carbon usage in technology, in this case in cloud compute usage. There's also in the economic space this global digital skilling initiative, which also has some funding opportunities. So take a look at those. I will put the links in the chat as well. Okay, other than that, we're going to jump into the talks. Please make sure to feel free to use the chat to ask questions of the speakers. And Roy, our host, will do a fantastic job as usual of reading aloud the questions during the Q&A part of each talk. So with that, let's jump over to Gavin Janke, our first speaker.
So I'm Gavin Janke. I am General Manager of Engineering here in Microsoft Research. And what I'm going to show you today is some of the background and science behind our family of devices. And so, okay, let's see, there we go. So when we set out the initiative, for our goals behind mass sensor deployment in order to get, very broad data capture of, air quality, is obviously we wanted to have accurate sensor measurement. We wanted to have devices that went directly to cloud, which meant that we wanted to be infrastructure minimal. We didn't want specific, radio, LoRa setups. We didn't need to have special power requirements. We want these devices to be low cost. We want them to be very easily deployed, so literally stick or hang and go. We wanted minimal service needs for these devices so that they don't need to be visited on a regular basis. And we also wanted to create a platform that was extensible. So taking all of these points into consideration, it took some considerable design and research into electronic components, the state of the art in terms of microprocessors and power circuits, that kind of stuff. So what I came up with was a family of devices, which started with the Eclipse Pro. And also the Eclipse LilyPad, which I'll explain further on, which is our water quality measuring device. So these are what I classify as infrastructure devices. And so these are typically in fixed locations. And we wanted them to be, LTE-M enabled. So we used Nordic's very latest NRF 9160 microprocessor. Which allows, cellular service SIMs to enable a device to directly connect to the cloud. They're incredibly power efficient. They use the latest Zephyr OS operating system. And our Eclipse Pro devices and the LilyPad devices are also Bluetooth LE enabled. They have their own Bluetooth microprocessor, so that we can do easy telemetry, capture, configuration, that kind of thing, without having to do everything through the LTE connection. These things have basically no infrastructure requirements, so there's no Wi-Fi setup, there's no LoRa radio setup, there's not even any power setup. They're incredibly power efficient, 100 to 300 microamps consumption in terms of battery usage. And, you know, we've come up with some technology using solar harvesting circuits and some latest state-of-the-art crystalline solar power panels, which are literally 3 by 3 inches, which I'll show you some more in a moment. So these things can be powered indefinitely based on the power usage budget that we set for these. The devices are fully sensor extensible. I'll speak more about that in a moment. And we wanted to get these around the $100 price point, you know, fully assembled, enclosures, everything. Then we also have the Eclipse Mini, which is a scaled down version of the Eclipse Pro. This captures both particulate and carbon monoxide. These are based on Nordic nRF52 microprocessors. So the goal is that these are paired to your typical smartphone. They're wearable personal devices. They have GPS capability within them, which are very accurate in terms of lat-long resolution. These sample at a much higher frequency rate, anything between 20 seconds or up to 10 minutes or longer. Typically, the person who has these wearable personal device would charge these at the same rate that they would do their cell phone or watch, so once every day or a couple days. Again, these are sensor extensible, and our price point for these, we wanted them to be in the kind of $60 range or under. So taking a closer look at our Pro device, so we sample 4 gases, so NO2, CO, O3, and SO2. We have a PM1, PM2, and 2.5 and PM10 particulate sensor. This sensor is a very high quality sensor that's made in Switzerland. We found that it to be incredibly accurate in terms of closely tracking our devices that were deployed actually at EPA station sites, so the correlation was pretty spot on. As I said, these devices are LTE enabled out of the gate, so they have their own 5G cellular antenna. And I'll speak more in detail, about the other features of this in a moment. So if we go into a deeper dive, so these devices are powered by Xbox. They have the Xbox Controller Elite's 2000 milliamp hour battery, which is rechargeable. And this gives us all of the compliance issues that we don't need to worry about. These batteries and systems are literally child-proof, blender-proofed, and everything else. So we don't need to worry about, certifying, batteries in this scenario. I designed this in mind to be a modular power system. So depending on the scenario, these can be powered by USB cable, solar, or something else. Could be plant powered. There are some scenarios where you can use the differential between wet and dry, or also thermally coupled powered. So we have the ability to swap out within seconds the power driving system within these devices. We found an incredible technology in terms of solar panel. This is a 0.6 watt, 66 millimeter square panel, and it can literally charge a depleted battery in a couple of days, just with some glimmers of sunlight. So assuming these are positioned anything between eastern and western exposure throughout the year, even with Seattle's dubious cloud cover, these devices can be powered indefinitely, even with a 20-minute or quicker sampling rate. We've done extensive airflow modeling within our enclosures to ensure that the air and the consistency of airflow movement for these are going in the correct way. Obviously, we don't want these devices to have stale air within them. And so our modeling has shown that, we get good airflow so that we have current up-to-date air in the enclosure when we're doing the sampling rates. These devices are easy to assemble, easy to take apart, and then the next part is the modularity. And so we wanted to be able to have these systems to be extensible without having to get the soldering iron out or to respin the PCBs. So using quick stemmer connectors, this is an I2C protocol wire and power standard that's quickly forming out there. We can literally add a VAC sensor, or we can make a device Wi-Fi enabled if we want to, that kind of thing. So a great extensibility story whereby multiple extensible modules can be chained together, and with simple firmware upgrades, which can be done both over the air, so we can literally push firmware updates over LTE. We have an incredible story around modularity, extensibility, and upgradability without even having to crack the case open with firmware updates. Another angle that we have been pursuing is water quality. And so based on the same operating system and hardware stacks, we have something called the Eclipse LilyPad. And this is one of our initial designs for that, whereby, again, with a set of extensible capabilities, we can measure all kinds of things when these are floating in the water, whether it's conductivity in order to do salinity detection, turbidity, pH sensing, obviously thermal temperature, and also other things. Using synthetic DNA, we could potentially tune into specific bacteria or algae growth in lakes and stuff like that. So in areas where there's questionable water, whether it is in the summer months where our lakes are certainly inundated with fertilizer runoff, which causes beach closures, in areas in poor parts of the world where drinking sources are easily polluted. The typical existing infrastructure for water testing is person goes out with a test tube, goes to the lab, several days later comes back. And so this new breed of devices can literally give live updates, again, within the 20-minute or quicker or longer cycles, depending on power budget, in a way that hasn't been achieved before without the need for legions of people with test tubes. And again, because these are connected directly to the cloud using LTE, I think we have a real innovation opportunity here for doing mass water quality sensing in all kinds of different scenarios, developing worlds or even our own world, especially with, hurricanes, and flood waters. It's very easy to get compromised water supplies. And there we go. There's our LilyPad in its fully lit up glory. Obviously, LEDs like that are going to blow our power budget, but that's a nice proof of concept of the kinds of things we could have. Glowing lily pads at nighttime telling us what the water quality is. We could say, oh my gosh, how glowing at the end of our dock. Not that we all have lakefront properties. We can obviously tell that something's up with the water beyond just LTE readings. Anyhow, so that's the end of my presentation. I will take Q&A questions after my co-presenter Miriam goes next.
Sorry for the delay. I believe my connectivity is somehow acting up right now, but getting through it.
Timing is everything. While we wait, Gavin, would you want to field one of the questions that's come in? And once Miriam has her presentation up, then we'll pass the mic back over to her.
Yeah, could you read that question out for me, please?
Sure. The first question is, have the Eclipse sensors been reviewed by the EPA or other third parties, AQMD?
No, we haven't gone to that step yet. Right now, we're just getting all of our calibration and, enclosure designs and everything like that figured out. we will be doing so shortly, but we feel confident about the accuracy of our devices at the moment, so it's pretty exciting.
Great. It looks like Miriam's presentation is up. So Miriam, we'll pass the mic back to you and we'll reconvene for Q&A at the end of the session.
Perfect. Thanks, Roy. Hi, everyone. My name is Miriam Berhane Rusam. I'm a senior program manager in the Azure IoT group at Microsoft. So in this short talk, I'll be providing an overview of the services that we provide in Azure IoT to really help transform, different businesses, researchers, and industry with a lot of the innovations that are happening. So as we all know, clearly we are in this new era of digitization across different industry, and we're seeing this wave of what we call digital transformation across, at this point, every industry, right? If we look at the energy sector, it's a daily talk around how do you become more efficient in operations, but also how do you provide cleaner power using less of actually maybe of the more traditional energy sources. If we look at cities and urban spaces, of course, creating more sustainable operations, infrastructures, and having cities to be more competitive is an everyday type of talk at this point. And if we look at things like agriculture, for instance, you start talking about how can you achieve better yields or higher quality in terms of the crops that can be achieved. So if we look at what are the innovations that are enabling these new opportunities and are actually solving the challenge that exists, it all clearly started with a wave of cloud, pretty much with the cloud being an unlimited compute resource where a lot of data can be acquired and centrally computed and actually managed, which all of a sudden provides a lot of insights. But as we moved along the journey, IoT came into the picture, which is this new ability to connect any asset, any devices. And so it kind of broadened the ability to acquire new insights from probably things that we were not able to have insights before. As we move along to that journey, it's really, once you have all this type of insights and data, AI starts becoming the really where the value gets manifested. And in a lot of cases, the combination of IoT devices and there is a need to really take actions also close to the edge. So we've also went to the motion of bringing AI actually closer to where the action happens for a variety of reasons, either because you don't need a loop back with the cloud to take actions, or there's privacy concerns, or there are bandwidth concerns, and so there's a lot of that action that needs to happen before the cloud gets involved. But we also progressed into what we call really in this innovation spectrum, digital twins, which is really connecting devices and getting signals from IoT sensors may not be sufficient in most of the applications, whereas being able to create replicas of what your physical environment looks like so you can take actually better action. And so we've been on this journey from Microsoft perspective and from Azure IoT perspective, really being at the forefront of providing this type of capabilities. We're investing $5 billion in IoT, and this is over a span of 4 years. And the goal is really to provide every customer the ability to transform their businesses with connected solutions. I actually really like the slide because even though it kind of shows an urban space, a city where actually a lot of the different industry are also happening and take action. So we'll also see a lot of interconnection, right, that happens on how decisions get made, on how data needs to be shared across different entities. A clear example between retail spaces and government, but energy and government, or automotive and government, for instance, right? So a lot of that synergy even needs to happen to enable a broader ecosystem, like a city. So from IoT perspective, from Microsoft perspective, we do offer a large set of products that actually enable, our customers, our partners, really to achieve their goals. So this slide has, comprises all the different offerings that we have, and it really goes all the way from, if you look from bottom up. All the support and services that we have for when we start talking about devices and edge devices, and all the way to the cloud services like Azure IoT Hub, device provisioning service, or digital twins, which I'm going to go in a second. But also going into more, how can we simplify it actually for anyone that doesn't have really, any enterprise or company that's not cloud native, or they don't want to spend a lot of time to build their IoT solution. So kind of more providing them a almost ready-made platform for easily building their IT solutions with very least expertise. So we made a whole journey around simplifying what it means to build an IoT solution. So I'll maybe with a few minutes, I'll go touch base on a few of these products. But before that, I just want to just talk about what it means to build an IoT solution. So when we look at the high level, right, it's a simple thing as you have a thing, you're connecting that thing, you get insights, and then you're actually taking action. But a more realistic view, really, when you start building an IoT solution at a scale, there's a lot of complexity that comes into the picture, right? So you're going to need to think about security, device lifecycle, disaster recovery, high availability, and there's a lot of this that needs to be considered, depending also how critical a solution is, for example. And so this is a reason why we're putting a lot of effort into simplifying what it means to do IoT, because it's just transformational for every industry. And at this point, every industry and a lot of enterprises and companies are looking at leveraging IoT to transform their business. So one of the guidance that we provided, we published this white paper to help customers, businesses, partners understand what it takes actually to build an IoT solution in such a way that can scale. There's these 8 attributes that we've considered, around scale, device management needs, big data management, because you're acquiring a lot of data. But also things like high availability and disaster recovery, security and compliance, and very important, total cost of ownership. And a lot of times when a solution gets started, someone is starting an IoT project, probably they're not taking into account all of this considerations. And so this is a great white paper to start to read and really have an architecture from the get-go that allows for scale. From starting with Azure IoT, we do have a couple of different entries according to the needs. So clearly, the first one here that you see, you can choose at using a number of PaaS services and actually build your own solution, your own SaaS, leveraging all the PaaS services. But also, if you want to get started on more of a SaaS platform, it's not a finished SaaS, but that quickly allows you to connect your devices, get the insights, and really act on your business, you can go with the option of building on top of IoT Central, which is more of a managed SaaS platform. If we look at a number of this type of services, if I see IoT Hub. It's key service in building an IoT solution, which is a cloud gateway that allows bidirectional communication for your devices. It's designed to scale for millions of devices in a very secure way. Also comes with a device, what we call device provisioning service, especially to take into account security and device authentication from the get-go. The second one, to quickly show you, I touch on IoT Central, which is a managed SaaS solution. And this is really for anyone that doesn't have any cloud expertise, really, and or wants to get started really quickly and doesn't need any high level of customization. So pretty much the experience becomes, provides you a whole surface for managing devices, and creating dashboards, acquiring the signals, and doing analytics. It works. It's based on all the IoT PaaS services from the first slide. The other thing that becomes interesting that I wanted to touch on this is also Edge, IoT Edge offering. And this is pretty much an offering that allows you to move any type of workload from the cloud all the way to the edge devices where the action happens. And so the beauty of this is that you could do a more seamless, right, compute or storage or any cognitive services that you can create them in the cloud, but then deploy them all the way to to the devices. So one of, for example, one of the example, if I look at especially at the applications of artificial intelligence at the edge, you could have any object detection algorithm, right, that can be trained in the cloud. But then the modules can be downloaded all the way to a device, an edge device, a camera, and a gateway. And really all the processing can happen right there without sending any of the data in the cloud. And probably what you're going to send to the cloud is going to be more of the signals, like counts, for instance, especially in a city, in an urban area. If you're interested about flows of different things moving across the board, this is a way to achieve it in such a way that's also privacy, achieves the privacy and not sending any PII information to the cloud. And so there's a lot of interest around that.
Miriam, I'm afraid that we are out of time, and I apologize. I know we had a few little technical glitches getting into this session, but thank you very much for your presentation. Luckily, we received some great questions, and our team on the fly has been responding as we go. So the question session is being tended to. Miriam, Gavin, thank you both very much. I'm sure that if there are other questions that we receive, you'll be able to answer them in due time. So with that, let's move on to our, thank you. Let's move on to our next speaker for the morning. That'll be Ron Cohen from University of California at Berkeley, who will be talking to us about quantifying urban scale carbon dioxide reductions and related emissions changes during the COVID-19 shelter in place. Ron, the mic is yours.
Thank you for the opportunity to chat this morning. So you'll see on this first slide that what I want to talk to you today about is the future of urban air. And we just heard some examples of how we might observe that air. So I want to sort of put that in context of some things we know about the atmosphere and how we, in the atmospheric science community, manage observations to learn what it is we want to know about helping governments and citizens manage their emissions and their exposure. So you see in this image the two things that we care about in the atmosphere most. One is climate change, and the other is air pollution. The two photos are photos of the George Washington Bridge in New York City, one from when I was a kid and one more recent. And just reminding us that we've made tremendous progress in managing air quality over the last 3 decades, and a large fraction of that has been managing emissions from vehicles. If you can go to the next slide. In the next slide, we see that I just remind you that basically what we have to do is we have to reduce emissions into the atmosphere. And in the next slide, I outline the key things that we need to do to think about that, which is if we know that we're going to, knowing that we're reducing emissions of chemicals into the atmosphere in the way we intend requires a really sophisticated combination of tools. And those tools are some way of making a prediction or a hypothesis about what the concentrations in the atmosphere are. And that requires we start with some economic and social data. That could be how much natural gas we use in our house and burn to emit CO2, how that connects to temperature outside, verifying that with economic data, how much we're paying to the power company for that natural gas, where we move in our cars. And then we need to take those emissions and move them into the atmosphere and understand what we might observe. And that requires some weather model with the accompanying chemistry. And what we're talking about here is how we manage that prediction so that we know it's right. So what tests do we do of that hypothesis with observations in the atmosphere that guide our thinking about how accurate those predictions are? If we had a perfect model, we wouldn't need to be making all these observations. So we need those tests with observations, and then we need a strategy for synthesis of the available information so that we know what's right and what's wrong about our prediction. In the next slide, I just show you some examples of that. So here's an example of economic and social data. You see estimates of CO2 emissions in the middle of the night, and you see all those dots are individual point sources, primarily power plants and oil refineries, with a background very low vehicle emissions on the highways. And then at 7 a.m. in the middle of the rush hour, you see that the highways jump out at you. And in the next slide, you can see a combination of that economic and social data with a weather model. And if you can click on the movie and run it, you'll see a prediction of CO2 concentration running over 3 days. You'll see a large source at the Chevron refinery in Richmond. You'll see high concentrations at night and low concentrations during the day. That's the interaction of the meteorology with the chemistry. So that puts it together. So that's the start, and then we need to think about how do we go about testing these ideas. And there are lots of ways that you might try and construct a test of those hypotheses. So one would be that you'd like to know what the total annual emissions are from a city. And that's often the reporting criteria for international agreements about CO2. But you might like to be more process-based and separate by activities. So you might like to know the different emissions from vehicles, from industry, from home heating, all your other favorite sources of emissions into the atmosphere. And you might, or you might like to know this, what's different about the emissions at your house from your neighbor's house a mile away, and how does that vary with time? Yesterday, there was a 5-alarm fire in San Francisco, and an aerosol plume from that came across the East Bay where I live with a county warning that came with it. That plume lasted about 2 hours, and it was about 10 kilometers wide. So here in Oakland, it was quite gray, and in Richmond, California, 10 miles away, you didn't see that plume at all. So understanding what resolution and what time you need is an important piece of it. In the next slide, I bring you to our strategy for thinking about this beacon and our hypothesis that dense networks of medium quality observations can be more cost effective and give more insight than a smaller number of state-of-the-art observations. And this was sort of implicit in what Gavin talked about earlier today, that having lots of observations gives you a new window into the atmosphere. But that we also know that really, really beautiful observations have been used for a long time. And we're looking at a trade-off between having almost perfect observations and then spending all the intellectual energy thinking about how we extrapolate those observations from a single point to all of space, or having lower quality observations everywhere and the advantages of that map. And that's, it's easy to say the map is better, but actually proving that is yet to be done. And so that's a piece of the work in front of us, is to establish that with the map, we actually get something that we don't already have in our hypothesis. So in the next slide, you're looking at green dots that represent each location in the Beacon network, the Berkeley Environmental Air Quality and CO2 Observation Network. At each of those dots, if you go down to the next slide, you'll see what we're measuring. We're measuring CO2, CO, ozone, NO, NO2, and particles. In the atmospheric science world, $6,000 a piece for these is low cost. Half of that cost is making a good CO2 measurement. So not at the price point that Gavin was talking about earlier, but relative to federal reference methods for these molecules, or the state of the art, this is about a factor of 10 lower cost than, or more than the equivalent measurements that are state of the art. Okay, so if you go to the next slide, what you'll see there is, and if you can run the movie, you'll see about 10 days of observations of CO2 from this network. You'll see lows during the day, highs at night. You'll see extra highs in the region that's at the entrance to the San Francisco Bay Bridge in the morning. And this is the typical sort of variation at the 1 hour average scale. And you see both the spatial variation and the diurnal variation. So we'll just let that movie run a little bit so you can see a few more days. Okay. Okay, we can pause it there and go to the next slide. So step one of this is to have a wide network and to drop the cost of sensing. But step two is to understand how you calibrate many, many sensors in many locations without the traditional way that atmospheric science has established the accuracy of measurements. So without bringing reference material and gas standards to every location where we make measurements. A normal strategy might be to calibrate every night at 2 o'clock in the morning with a known standard. So that's the real key. And the sensors aren't low cost unless you drive the labor cost of that calibration process down to be comparable to the cost of the sensors. So if you had to spend 10 people to calibrate 60 sensors, then it's not worth having the inexpensive ones. You might as well have expensive ones. So these two papers that I reference here are examples of how we've gone about trying to establish strategies for calibration of CO2 observations and the electrochemical air quality observations of a different manufacturer source than Gavin showed you, but the same basic principle of operation. In the next slide, I just want to start by giving you an example of what we can do with this network. And it's an example that is from a paper that Alex Turner, who's on the line with us, just submitted. And the question is, how much did CO2 emissions drop in the early phase of the shelter in place? And why did those emissions drop? So if you go to the next slide, what we need to do to answer that question, or what we did, was to take all the observations that I just showed you and do a systematic mathematical inversion between the observations and our hypothesis of what the source was. And, you know, in one way of saying what the steps of this are is, step one is to take every observation and map it to the family of locations where those CO2 emissions came from. And step two is to do some kind of weighted analysis where you estimate the combined model and observation uncertainty. Neither is a perfect representation of the world. And step three is to maintain a physically reasonable solution by imposing correlations in space and time. So it would be unreasonable to say that there were, you know, the emissions from cars on a highway were corresponding to 10,000 cars today at 7 a.m. and 0 at 7 a.m. tomorrow and 10,000 again the next day. So we expect that there's some smoothness in the variations. And then we adjust the emissions to obtain the best predictions of the observations from the network. So I just want to give you a little bit of a flavor for what this looks like. So if we go to the next slide shows you the algebra of the Bayesian inverse that we're doing. So XA are the estimate of what the emissions are. In the language of this work, that's called the prior, but it's basically, that's our hypothesis. And it's the estimated emissions in space and time at every point in the domain that we're trying to analyze for. If you go to the next slide shows you the observations. So here's CO2 observations before and after the shelter in place, highlighted in purple and green. And you can see, you know, you also will notice that we went from winter to spring during this time period. And the variance in the observations in winter is much higher than the variance in spring. So one of the things that happened early on in the analysis of observations all over the world from the shelter in place is people mistook the enormous changes in the atmosphere that happened because spring happens for changes in emissions. And both things happen simultaneously here. And so the reason we have to incorporate the weather model is we have to take into account the differences between spring and between the observations. And then if you go to the next slide, here we're showing you just the average of the observations before and after the shelter in place. Purple before, 6 weeks before, and we left out the week of the transition, and then green the 6 weeks after. And you can see that it's not subtle, that during the morning rush hour especially, there were enormous decreases in CO2 in the atmosphere, but pretty much all day there were decreases much more during the week than on the weekends. Okay. So if you go to the next slide gives you an example of thinking about the emissions. So you'll see a set of blue lines in this slide. Those blue lines are trajectories that indicate where the air came from for one observation in the network. And because the atmosphere is turbulent and a model is an imperfect representation of that unresolved turbulence, we create a situation where we generate a statistical ensemble of possible paths backwards. And so it's not a unique one-to-one mapping between emissions and the observation, but we try and capture the range of possibilities and statistics associated with the turbulent atmosphere. Okay, so in the next slide, just remind you that we have those back trajectories, and I showed you one, but what we need is a back trajectory for every observation we're trying to analyze. And I told you that was 6 weeks before and 6 weeks after the shelter in place started, and it'll be for every point inside that box shown on the left slide. Okay, and the white line in the right image shows you the region of most influence. So where the combination of emissions and those back trajectories that I showed you in the previous slide, where's the most important set of those back trajectories. So you can see that the region of influence where we'll have the best sense of what the emissions were is encompassed by that white line. Okay, so the last piece of this that we have to build then is some understanding of the covariance between the errors, and that's a matrix that represents the errors in our measurements, errors in our representation of the background outside the domain that we're modeling, and errors that represent the model error inside that domain. And that's, okay. So in the next slide, labeled systems of equations, I just want to give you a sense of the computational effort that's going into this. So in this example, let's say we're trying to do 2 weeks of the 6-week period. So we're going to try and get hourly fluxes at about 1 kilometer resolution for 15 days. So that's in this domain that we're showing here, that's 157 kilometers by 121 kilometers in area. And it's got, there's 360 hours in 15 days. So that's 55 megabytes of data that we're trying to manage. That's the size of the matrix that we're thinking about doing an inverse on. If you go down to the next slide, one of the challenges then is that the error covariance matrix is then M by M, so that's the product. And so a strategy for making that manageable, inverting a 374 terabyte matrix is hopeless, is to represent the space and the time variation separately. So we do that as a way of managing the computational effort required to do this matrix inversion and solve the problem that I just described to you. Okay, so in the next slide, we get to the answer. You see 3 panels here. A panel before the shelter in place, so our emissions, what emissions looked like in January and February, early March. Then in the middle, how they changed after the shelter in place. And you'll see that that's not as purple, especially at the entrance to the Bay Bridge, sort of in the center of that panel, but all along that highway. And then on the right panel, see the difference. You see the difference is concentrated on the highways, but there are differences in other locations. And again, in this region bounded by the black line, we have high confidence in the change that we observed, and the region outside that line, our observations have less influence. So the emissions you see are mostly the prior. They're mostly our initial hypothesis. If we go down to the next slide, we can add up all those changes within the boundaries of that black line and look at what we see by sector. So starting from the top, the black line you're looking at is the total emissions averaged for each day of week and time of day. So you see in this that the total emissions are at a minimum about 300 tons of carbon an hour, and they get up to as high as maybe 600 or 700 tons of carbon an hour, peaking. You see in the orange line that most of the variation with time of day and day of week is due to traffic. That there's a category we call other anthropogenic, which is home heating, refineries, power plants, and other industry. Those things are relatively smooth and not changing over the course of the day. And then you see uptake of CO2 by the biosphere, which in this analysis we constrain to observations from a satellite. Those are changing, but they're changing too slow on a weekly timescale for you to see. But you see the winter-spring difference by looking at the upper panel and the lower panel. In the lower panel, you see how much lower the traffic-related emissions are, whereas Before the shelter in place, the minimum in the traffic-related emissions was most of the time above the 180 tons of carbon an hour that were associated with the other anthropogenic term, the purple line. Now you see even in the middle of the day, most of the time we're at or below the level of that other anthropogenic. You see a dramatic decrease in the rush hour emissions, and some change also in the weekend emissions, but smaller amounts, percentage changes on the weekends. So if we go down to the next slide, I'll point out just one more thing that I'd like you to note. Before the shelter in place, there were lots of emissions at night. It'd be common in atmospheric science to say that, nighttime is a time when the atmosphere is too poorly constrained in terms of the meteorology for us to really get at the emissions at night by an inverse. And what you're seeing here is, in this case, we feel we're doing pretty well. We see changes in emissions at night that they were substantial before the shelter in place, and they dropped to almost zero after, and that's consistent with the flow of traffic. Okay, so I've tried to tell you something about thinking about emissions on the neighborhood scale, about an example of a dense observing network, and then strategies for using the information from that dense observing network to learn about emissions in the case of the COVID example. So I want to turn now to, in the last couple minutes, to thinking more broadly about what our community needs to do to make dense networks a tool that's widely applicable to cities. So if you go to the next slide, or skip 2 slides really to the one with the diagram, we're at the beginning of understanding about how to use dense networks as part of our system for air management. And I put here sort of in the interior of this diagram, in the red and pink box circles, the kinds of things that are tools that we use to understand the air, and then surrounding that, the applications that are important. So we're thinking about dense networks in a matrix of other ideas about models that are at the scale of those networks, and data science that might reduce the computational effort needed to interpret the observations, and other observations that are not at the surface, satellites and remote sensing or aircraft observations. And then the things that touch on the air, which are greenhouse gas management, air quality, epidemiology, and health, giving communities control over their air and the politics connected to their air by giving them direct knowledge of which emissions are affecting them. And then, outside either urban ecosystems, or a lot of these same ideas would apply outside of cities. As we heard, Gavin talked about rivers as another example where inexpensive networks of sensors might be valuable. So if we go to the next slide, I just want to, in our group, we're really trying to think about the science and how you establish that dense networks are the right tool to answer some of these questions. And some of the conversation we're having in this meeting is, translating that to a product that's sold by Microsoft or other people, or used by governments, for example, the EPA or a state EPA. And so I want to think a little bit with you about what we need to do to make this transition from the fundamental research to investigate how to do this to an operational. And you saw, in Miriam's talk, you saw some examples of how Microsoft is thinking about that in the Azure IoT world. You saw product design going from initial concept to all the different things she suggested that we need to think about to create an Azure IoT product. And here we're thinking about the same thing. We're just taking a step back and saying, I'm not convinced we're ready to have a product yet in that sense, because we don't really know what the network design is or which instruments are right for the right question. And so I'll just lay out in the last slide before I wrap up and thank you. So there's a list here of things. It starts with hardware, goes to calibration and maintenance. And then the other things we need that go from, doing this in a single place to scaling from pilot cities to widespread adoption. And in the middle of that are things we have to do about interpreting the observations and communicating them to stakeholders, committing to the education and workforce development that allows the kind of engagement of people with making this work. We're talking about lots and lots of people in different cities making use of observations in a way and information and giving them the information to make decisions, and that won't happen unless we educate them about the strengths and weaknesses of the information we're giving them. So with that, if you move one more slide, I want to thank all of the people in my research group who make this possible. Work I showed you today was mostly work of Alex Turner and Helen Fitzmaurice, but all of the other people on this slide were major players in the development of the Beacon network, or are about to be players in what we do going forward. And I'll close by thanking you for your attention.
Thank you, Ron. Thank you, Ron. That was a lot of information. Some might call it densely populated information, and appreciate the overview of the project. We have time for one quick question. And the question is, can you comment about any specific protocols you have for looking at wildfire smoke in urban environments, both in terms of specific measurements and also in terms of protocols to alert the public to risks? But we just have 1 minute for an answer.
We have no specific protocols. We haven't viewed ourselves as a real-time warning system.
All right, well, that was a quick answer. So thank you for that. And thank you again for the talk. Our next speaker is Charlie Catlett from the University of Chicago and Argonne National Laboratory. Charlie will be sharing thoughts on how cities can become smarter, sensors, edge computing, and the array of things. Charlie, take it away.
So thanks for having me as part of this. This has been a great workshop. I want to talk about the array of things, which is a broad project that began really back in 2013, and give you some idea of where we came from, what we've done, and where we're going, with an emphasis on the focus of the project, which has really been edge computing to analyze data right next to the sensors. We were motivated to do the project from talking with lots of urban scientists, including folks like Luis Betancourt and others, about the nature of cities and the fact that cities are collections of neighborhoods with very different properties and a very different experience depending on where you live. You see a couple of examples of that heterogeneity with Chicago here, from life expectancy to how easy it is to get into the center of the city by public transit and the access to services there. The green parts, it takes 30 minutes. The purple could be an hour. Yellow could be an hour and a half by public transit. So very different experiences, very different neighborhoods. And we began to ask the science community through a series of about half dozen workshops, and residents and community groups and different layers of people within the 9 layers of organization of the city of Chicago, in order to answer the kind of questions you are asking, whether that's as a policymaker or as a scientist, or in order to address the things that you are concerned about as a resident. What would you want to measure? And we got long lists of things that people wanted to measure, some of which we could do with low-cost sensors. Others we couldn't do with any sort of sensor, or at least not practically speaking. There are ways to do traffic flow with hoses that go across the street, but there's not. That's something that you really would normally observe. And in fact, that is the way that traffic measurement is done today, is people standing on the corner with clipboards or special devices to count. And so we separated these observations out as things that we would need to use computing to process the data in order to get the measurement, as opposed to the sensors where we're just reading an electronic sensor. Those capabilities or measurements translated into the specific sensors that you see on the screen here. We built the first units in early 2016, and they started going up in late 2016. I've got a map of the devices coming up here. And then we really concentrated on how we could provide a way to program these devices with embedded computers to do what we call AI at the edge, to look at some of those observations. And we started with just looking at very simple observations like the number of vehicles or people that are in a given scene every, certain number of minutes. One of the reasons, as I'll point out later, that edge computing was important is because, remember, this was back in 2015 or so, or 2014 when we proposed to do this, and there was no low-cost way to connect these sorts of devices. And so part of our motivation was we got to get a lot of data out of these machines without sending lots of data over the cellular network, which was and still is fairly expensive. So that was one of our motivations. Another, as I'll talk about later, is privacy. Ron just gave a fantastic talk on what they're doing there with the Beacon project and other things. We've had a couple of air quality groups that have helped us with calibration and trying to understand the data that we're getting from sensors that are probably a step below the ones that the Beacon project is using. Those $6,000 devices just with the air quality are still twice as expensive as our devices, so our sensor budget is fairly small. This is an analysis you see here. There's a link to a interactive page that the National Opinion Research Center did. This is a group of it's a group of about 300 data scientists in a large organization called NORC at the University of Chicago, and they were trying to ask the question, what have we seen with the COVID stay-at-home order, which in Chicago was about the third week of March. They ran into exactly the same thing that Ron mentioned, which is that there was already going to be a drop because of seasonal variations. And so although this slide shows just 2020 on that website, there are other graphs that compare 2019 to 2020. And then some publications on the right that have come out of that work. A big part of the array of things, and I would say we were trying to learn as much as we could about the notion of putting technology experiments out in the public way. And one of those is, how do you get hundreds of devices up in a city? And we ended up with a very good partnership with the city of Chicago and several departments there that put most of our devices up for us. Some of the challenges here, the basic challenge of trying to build things in quantities of hundreds is that we had to hand off all of the technology and training and build tools and test tools and protocols for dealing with unexpected things. We had to hand all that off to a factory to build things for us, and that really was a big challenge. A related challenge is building a bespoke system like this and enabling it to survive harsh weather, some of the moisture issues that we run into in anywhere that there's precipitation. And then what we were a little bit surprised about is that the Department of Transportation and specifically the Department of Electrical Operations, their life of power out to the poles is different than a resident's experience or a machine room experience. Is that they're just completely used to having dirty power and power that comes up and down. And so we were surprised at the reliability issues that all of the devices on these poles have, and they certainly are shared by our project. Some of the things that we've been talking about here, I'll just blow up that image there. That's about 130 devices that we have up today. There's been some turnover. I think we've probably deployed 250 or so, and there are 130 that are still there that we didn't swap out for newer ones. We're about to do another 40 or 50 as we've run out of NSF funds for the project. So the idea is to push 40 or 50 new devices out there over the summer to replace some of the ones on here that are older. Our discussion with Microsoft Research really began with their nice little device that Gavin talked about. As we were interested in placing hundreds of these lower cost devices out through a city like Chicago, and have been talking for a couple of years now. We have an open offer essentially from JC2Co to put a sensor of any kind on their bus shelters, modulo restrictions on the appearance of those devices and their functionality. But the JC2Co runs 2,100 bus shelters throughout Chicago, all with power. No networking to most of them. I'd say probably a quarter of them have some form of communications network, but this is where we were excited to see something we've been waiting for a while in low-cost air quality sensors, which is the cellular connectivity and the battery power that Gavin talked about. There's another project we've been working with a guy called LJ Chen at Academia Sinica in Taipei. He has a project called Location Aware Sensing System, or LASS, where he's put about 10,000 PM2.5 sensors around the island of Taiwan and throughout Southeast Asia. And it was his work with a $30 particulate matter sensor that caused us to decide to go with the latest batch of our devices last year with the same $30 sensor, very rugged, low quality, if you will, low cost. But some of the things that LJ is doing is using a Raspberry Pi as a platform and doing a little bit of machine learning at the edge to look at the history of the readings of a particular device and incorporate that into improving the data. So that's where we are in terms of deployment. That City of Chicago deployment assistance was part of the cost share, which was a 30% required cost share by the National Science Foundation as part of their major research instrumentation program. And the city provided the installation for free and has told us repeatedly, you know, of order 100 devices a year, we're happy to go out and put stuff up or swap stuff out. So we have this ongoing deal with them that has survived through 4 different Department of Transportation commissioners, 4 different CIOs, and 2 different mayors. So the notion, as I mentioned up front, of talking to people at all 9 layers of the politics has worked out, because although we've had turnover up and down that line, there's a persistent collaboration going on. All of the Array of Things data, not just the sensor data, but also we publish internal data about the devices, memory use, CPU, uptime, things like that. All of this data is open and free, and it's in a couple of different forms. One is a download site with the link that you see that you can get to from the project webpage. The other is an API. The download site is updated every night or around midnight UTC, whatever time that works out to here in Chicago. And so the data could be 24 hours old. The API gets data updated every 5 minutes. I'll mention, since I'm saying all data is open and free, there's a privacy policy that was particularly important to the culture of 2015 before people figured out that the real privacy risk wasn't a camera on the street corner, but the device in their pocket. We put together a privacy policy that says we will do all of the image processing and sound processing within the device and not send the data back to some cloud where policy changes might cause it to be revisited later with a different policy than when it was collected. The exception to that is that we've been able to download regularly, roughly every 15 minutes, an image and a sound clip And that, as part of the privacy policy, we have to keep that secure. You have to sign a data use agreement and have a write-up of what research you're doing with the data. So it is available for research, but is not published openly. By the way, I'll mention that just a side note on COVID, Argonne National Laboratory, so you saw in the title slide, I've actually taken sabbatical from Argonne and UChicago to work at the Discovery Partners Institute, which is a University of Illinois institute, but has partners in Chicago, including Argonne and Northwestern and UChicago. So as a side note, Argonne, which on a peak traffic day will have 5,000 people, Argonne shut down at the end of March. And I'll go back to the slide here. Argonne shut down at the end of March, and we, as a laboratory, were trying to figure out how do we provide some form of, sort of job security to the hourly workers at the site, which are many. And one of the things that we did was our machine learning and computer vision group scrambled and put together an image and sound annotation capability and trained a bunch of the Argonne hourly workers so that although they weren't doing their normal job, they were doing a job. And so we've been benefiting from their help there, and they've benefited as well. So governance, which is kind of a not a word you hear a lot with sensing. Maybe our motivation here was as I mentioned, in 2015, people were pretty concerned about cameras and surveillance in that fashion. Now they're a little more used to it, but I wouldn't say the concern has gone away. Really, for us, it was how do we ensure that when we do this project, that residents are actually excited about it and excited enough to say to their kids, hey, you should check out that sensing network, or excited enough that a teen or another youth would see the devices, which are fairly conspicuous, and say, that's really interesting. I might want to figure out how to do edge computing or atmospheric sciences. And so part of that was the policies, and those are published at our website. We haven't had to change them since we published them in August of 2016. A big part of why those policies work is that we put together a very diverse set of advisors that are the external advisory sort of board, and you can see them here. We are collecting chief information officers. On this picture is the current and the past two chief information officer for the city of Chicago, but we've got others, Alyssa Tenney, for example, president of the School of the Art Institute of Chicago, and Lynn Osmond, who's the president and CEO of the Chicago Architecture Foundation. So this has been a very important group for us to just sort of manage the project in the context that it's happening in the public way. So these are the configurations of, you can see our very conspicuously designed devices there. They were designed by the School of the Art Institute of Chicago. On a pole, I'll give you another lesson learned. We really learned the hard way that you want to get function right before form. And I was nervous up front that these would be big and ugly, and the mayor would say, you can't have those on my frickin' poles, or however Rahm Emanuel would phrase it, similar to that. And so we went with a small box, about a liter of space in to put the processors and the upward-facing sensors. That turned out to be a thorn in our side throughout the project. With the new projects called SAGE, we've gone with a much larger box. When you see these up on poles, though, they're pretty tiny. They're smaller than the walk, don't walk signs, even though they look big. They're about 14 inches tall. They stick out about 13 inches. They're about 9 inches wide. You can see some examples of the field of view and object recognition down in the lower left there, using downward-facing camera. On the new devices that we're doing with the follow-on, the SAGE project that I'll mention, we're going with professionally packaged cameras in those domes that are panning, probably not zoom, much more expensive, but also allows to have a much broader field of view. You can see here the field of view is about the size of a baseball infield diamond. They're have already been cases where we said we just need a different field of view, and this is one example is the Illinois Department of Transportation asked us to place these at some railroad crossings that are at-grade crossings, because while they know when the gate goes up and when the gate comes down, they don't know how many vehicles are affected, what kind of vehicles, they don't know how long it takes for traffic to get back to steady state. And so they wanted us to use machine learning to analyze the row of vehicles that queue up at a at-grade crossing. And the other example is that the Chicago Park District has many things that they're interested in observing, like patterns of use on bike trails or at beaches, or even just whether a park is being used at all, because they don't have a way to measure that. And for those projects, we need a much larger field of view than what we have here. So that's sort of gone into the design of the next project. So I mentioned AI at the edge, and our basic approach here is to see that while the sensors that we have, and a PM 2.5 sensor or a light sensor or even a camera are, they're fairly low bandwidth. We've been working with scientists who want to put hyperspectral images, for example, or LiDAR devices with much higher bandwidth. And so besides the privacy benefits of doing the processing at the edge, we also can deal with the bandwidth limitations that are going to persist even as always happens when things get faster. We'll find ways that 5G won't be fast enough, and certainly hyperspectral images will have difficulty. There's another aspect of the project that really is sort of, I guess, camouflaged in the fact that we have so many sensors, is that really what the project has been focused on is how do we provide an environment for people to do research where they want to make real-time decisions at the edge. When we were thinking about cameras and processing, we were not thinking about controlling intersections, but we were talking to transportation researchers who were saying we would at least like to experiment with detecting and reacting to things at an intersection in a shorter time frame than you could do if you send all the data back to the cloud. So that's a number of the different motivations that we have to doing AI at the edge, and again the idea of a platform that is programmable. And one example of, if it's programmable, we call this a software-defined sensor, then we don't have to decide ahead of time all the things that we might possibly measure. That can change over time. And I can say with great confidence that in 2015, we never thought we would want to look at images on the corner and say how many people are wearing face masks, but it turns out that might be a useful thing to do. And it turns out that is not a terribly difficult problem, except for when you're talking about or looking at a situation where the person's skin color is the same color as the mask. We also wanted to look at social distancing, but we don't know the 6 kids in the middle frame there. Maybe they're all brothers and sisters, and so it's okay that they're not social distancing. So there's information that we don't have. I think I just got the flag that I need to leave room for Q&A, so I'll just acknowledge that, unless it was a flag that says you can't hear me, in which case we're all in trouble. So there are other things we want to do with AI and vision at the edge. These are some examples here. This question about wildfire smoke, we actually do have in the upper left there, some of our students this summer looking at wildfire smoke, and can we tell, it's already hard to tell cloud cover, something as simple as that, with just simple computer vision or snow depth, but is it a cloud or is it smoke is another sort of challenge. So there are lots of computer vision challenges here. And then going deeper than just, what's in the scene and trying to understand the scene, one of our colleagues, Mark Berman at UChicago, has been using AI to examine not just images from Array of Things, but even Google Street View images and characterize them according to natural versus urban or ordered versus disordered. And part of that is to support research and understanding how the urban environment affects people cognitively and emotionally, behaviorally. And so we thought, and this was proposed as part of the follow-on SAGE project, but we were scoped down. So we'll come back and get this after we finish what we were scoped to do. But the idea was to put a set of measurement devices like the Array of Things, but the better ones that we're building now, in similar venues across the world in different population sizes and different climates and different cultures. The only ones we don't already have are New York City and Paris. We don't have in DeKalb, Atlanta, Nashville, Chicago, Taichung City, or Bristol. We don't have a similar venue in each of those, but we do have partners there that have put devices up. And of course, these vary in population from DeKalb, which is where Northern Illinois University is. That's probably a town of 30,000, to Taichung City, that's larger than Chicago. I've mentioned the SAGE project, so let me close out by just talking about this project, which is a sort of follow-on with the Array of Things team plus others. We partnered with the National Ecological Observatory, and we partnered with, of course, ourselves, the Array of Things. We partnered with UCSD, the WiFi HP-REN project there, which has about 100 towers in Southern California that are that have cameras and other sorts of sensors on them. And an example of what we want to do with AI at the edge is, imagine that you have a process that's running out the edge that's analyzing the smoke that's coming from perhaps a wildfire, and is sending enough information back to a supercomputer somewhere in the cloud that's running a model of the wildfire that you're observing, and that can get near real-time updates from the sensor network, from the SAGE devices, and adjust that wildfire model, the sort of digital twin of the wildfire, and possibly give actionable information and safety information to the wildfire crews that are fighting it. And with NEON, it's similar. They have some instruments that there's just no way they can get all the data back, and so they are forced to throw data away and average data. And what they want to do is they want to say, okay, fine, we're going to average the carbon flux or whatever we're measuring, but when something interesting happens, we want to change the way that we're sampling. And so they want the intelligence at the edge to determine that, quote, something interesting has happened, and then change the way the sensor behaves. And that, with respect to LiDAR, the idea there is, as you're sweeping the horizon and you see something interesting, you stop on that interesting thing, and then you increase the resolution of the LiDAR device. I'm going to, sort of skip through this. The idea here is we are shooting for the inevitable future here that we're seeing of billions of small devices, 5G or otherwise connected, all the way up to, hundreds of HPC systems. And what is the programming environment that you need to develop in order to make use of that if you are an atmospheric scientist or a transportation researcher or a social scientist? And so the SAGE project is it's a $9 million mid-scale research infrastructure project. They gave us about half of what we asked for, which was the development half and the prototyping half, but not the deployment at scale half. So we are viewing this as step one. And we've defined the cyber infrastructure based on the different user communities that you see, the 4 boxes at the top, of what is it that you as a scientist want to be able to do with this continuum that we've described. And then underneath that, the green and other colored icons there are the answer to, what is that cyber infrastructure. All right, so thanks for your time. Just a summary, this SAGE project and AI at the edge, we think is one of the ways that cities can be smarter by getting more and more diverse measurements in complementary things that you've heard already today. So thank you.
And thank you, Charlie. A lot of information, a lot of very helpful and interesting information. We do have time for a question or two. The first question that's come in is, how much has the cost of the devices dropped from the initial design to the units you're putting out this fall?
Yeah, so generally you would see the cost go down for 2 reasons at least. One is that you miniaturize, and 2, related to that, is that you get the scale of manufacturing. Those benefits have never kicked in with us because we didn't lock in and miniaturize because we felt that we needed to be able to continue to modify and debug. And we've only manufactured a total of about 350 devices. So we're an order of magnitude away, maybe 2 orders of magnitude away from those prices going down. For the Sage project, the price will go up because we're moving from 2 $60 processors to a couple of several $100 processors with NVIDIA Xavier follow-on chips. And the cameras will go from sort of $50, $60 cameras to $800 or $900 cameras. We have still an exercise to do that has been set back a bit by the fact that we can't do meetings in person anymore. And that is to revisit all of the air quality sensors and try to go with higher quality air quality sensors for the for that part of the project. And because the new devices are fully modular, that can be done in parallel with all the work that we're doing on the compute box, and then plugged in with power over Ethernet whenever the sensors are ready.
Great, and then we have 2 more questions. We'll see if we can get through both of them. The first one is from Sean Jansen, and Sean asks, lots of great presentations on IoT devices this morning, thank you. However, I'm not hearing much about the security of these devices, and any security mention seems hand-waved. Yet, hacking smart city IoT devices remains a credible threat. One of the big challenges of smart devices is being able to patch them without having to make physical adjustments across thousands of devices. For any of the speakers, what approaches are being done to secure these devices?
So I'll just jump in and thank you for the question. So our security was day one part of the architecture, and there are a couple of aspects to it. Signed code, encrypted communications, but the biggest one, and that's been a challenge, is that these devices have no open ports unless somebody makes a mistake, obviously. And so they're running, and the only way we can communicate with them is if they establish a tunnel back to us. So they're programmed so that they wake up, they call the mothership, they can only call the mothership, and then we get the data when they do that. As far as patching and things like that go, that's also been part of the scaling effort in our project anyway, to be able to update these devices, assuming that they phone home, right? Update these devices as readily as we would update all the nodes on a compute cluster, and using some of the same tools.
And with 1 minute to go, we'll see if we can squeeze in the last question. Regarding privacy and people's perceptions of technology, what are your recommendations for conveying to the public what the sensors are actually doing?
Oh, I think that's simple. You tell them exactly what the sensors are doing, and you be completely transparent on what they can and what they can't do, and what is the difference between the sensor can't do this and we've limited the sensor so that it can't do this. So one is a technical limitation, the other is a policy decision that could later change. But what we find is that's a dialogue that you just keep just keep having, but transparency is really, really important.
Great. Thank you very much, Charlie. Appreciate the comments and the responses. Our next speaker is Edmund Sito from University of Washington. Edmund will be talking about community air quality sensing, what we've learned from calibration and crowdsourcing studies. Take it away, Edmund.
Today I wanted to talk a little bit about my experience with air quality sensing, less as an atmospheric scientist and less as a technologist, and perhaps more as someone who's coming from a public health background, someone who's interested in people's exposures and how they affect people's health. So, that said, I've been involved in developing and deploying these sensors for quite a long time, and so I wanted to share a little bit about how it was in the early days and how it's evolved over time. And so in the early days, the situation was kind of like this. We're in California, and then we gradually migrated over to Washington State. But when we were talking to the environmental monitoring agencies, so in California, it was the California Air Resources Board. In Washington, it was Puget Sound Clean Air Agency. There was always this hard sell. If you look at their budgets that they spend on air quality monitoring, it's $100 million per year in California. In the Puget Sound area, it's about $30 million per year. And what we were talking to them about were the emergence of these low-cost sensor systems, which are $10 each. So while on one hand, I was hyping the excitement and the paradigm shift, if you look at these population numbers, you can envision, if you do the math, it's every single household in California having their own air quality monitor, as opposed to, like in the Bay Area, it's about 20 sites for 7 million people. And so it really would be a paradigm shift if we could get a large number of these sensors to people, to sites, to communities. And the response that we always got, as a researcher, we're submitting proposals to the US EPA, to CARB and whatnot, was always, is this too good to be true? You need to show us the quality of these sensors before we'll believe you, before we'll invest in doing large-scale network deployments. And so naturally, that led to a lot of performance evaluations of sensors. And if you look at the literature, there are still ongoing studies that are being published that are papers doing exactly these kind of experiments. So this is a government monitoring site. It's operated by the California Air Resources Board. It's in Southern California. And if you zoom in to their rig up at the top of this station, you'll see we've co-located one of our community air monitoring boxes on their rail there. And the idea is that, if we need to show the performance of our sensors, they need to be shown in relationship to trusted standard instruments that the government uses. And so you'll often hear terms like federal reference methods or federal equivalent method instruments. These are US EPA standards for not only specific kinds of instruments that they would use, and in this case, these are particle instruments, but also the operating protocols, as well as the QA and QC methods that are employed. So it's the whole gamut of ensuring that the data are of high quality. And so we wanted to show that what do these $10, on the order of $10 sensors might do in relationship to what's traditionally done. And so over time, we collect data that looks like this. This is a time series of particle monitoring data from an instrument called the DILUS, which we were using at the time. And it was co-located against beta attenuation monitor, which is one of these FEM or federal equivalent method instruments. And if you squint hard enough, you can kind of see some correlation between these time series, these dot patterns above and below. And it's a little bit helpful when you model the correlations and you show them on a 2x2 scatter like this. And so on the left, it's a comparison of the DILUS versus the BAM for PM 2.5 measures. And on the right, it's for larger size particles, coarse particles, PM 10. And this was, it's probably not the first glimpse, but it was one of our early glimpses of the performance of these lower cost technologies, which are suggestive that, an R squared of 0.8, that there could be some value in deploying these. Perhaps we wouldn't be able to use them for regulatory purposes, but in terms of public health purposes, maybe there could be some value here. And then in terms of convincing people, one of the interesting political things that we did, science politics, is we were open about sharing our data with the California Air Resources Board. And we worked with them collaboratively to actually do this data analysis, with the thinking that, if there are people that we needed to convince in California, the California Air Resources Board would be some good people to convince. So we've continued to do these co-location experiments, but for different reasons, different than our earlier goals of demonstrating performance. One of the things that we've done in sort of our laboratory has been to look at sensor quality. And this is some early work that we did just in a laboratory chamber where we had control over the kinds of particles that we're releasing into the chamber. And you know, we plumbed in a reference instrument, TSI APS is our reference instrument here. And we just had replicates of this low-cost sensor. In this case, it's the Xingye particle sensor. And we had 4 of them. And they were all exposed at the same time, side by side to one another, to these sort of standard aerosols, 1 micron polystyrene spheres. And you could see there's some quality control issues with sensors directly from the manufacturer, at least for this particular one. And these were all ordered at the same time, so they're from presumably the same manufacturing batch. And so this is a problem. If we're deploying these in the field, the fact that they're off by 10, 20% sometimes directly from the factory means that we need some sort of quality control process internally, either before we deploy them or as we deploy them, we do these co-location experiments so that there's some calibration. The other thing we've observed, I showed that previous plot was from the Xingyes, is with each new generation of low-cost particle sensor that comes out, these days a lot of people are using low-cost Chinese particle sensors. And so on the left is this Plantower sensor versus the Xingye that's on the right. You could see that there's a lot better attention that's paid towards quality control because the use cases are different. I think the sensor manufacturers are recognizing now that we're deploying them not in air cleaners or in range hoods or whatever, in whatever sort of industrial gadget, but rather we're actually trying to use them for this new use case of community air monitoring or regulatory monitoring in some cases. They need better quality control out of the factory. And so we're seeing that now with sensors like these Plantower sensors from China. This was an experiment where we had boxes with replicate sensors deployed in the field. So you can see, the 2 Plantowers are compared to one another. Both of those Plantowers are in the same box. And similarly, in that same box, we've got 2 Xingyes. And so you can see how much noisier the previous generation Xingye type sensors are compared to the current generation Plantowers. And as you'd imagine, there's Xingyes, there's Plantowers, then there's X, Y, and Z. We've seen now an explosion in different sort of, particularly for particle sensors, different makes and models of particle sensors. And so you'll see this is not my group's work, but this is another research group's work where they've started to compare, again, with these scatter plots, what the relative readings are from these different makes and models of sensors. And you can see that they're all slightly different. So again, it raises this issue of calibration and quality control of measures once we deploy in the field. And the market is just continuing to explode. It seems like every 6 months there's a new batch of new commercially available particle monitors that people are developing. And generally they all perform quite well. And so that's very good to see. Another reason why we co-locate. So it turns out that with the government FRM and the FEM methods, generally the operating principles are mass measurements. And so the units that you get out of those instruments are microgram per meter cubed concentrations. It turns out that most, if not all, of the low-cost PM sensors tend to measure light scattering, which is not mass. And there are some issues with light scattering measurements. This is a paper by Chakrabarti et al., not my group's work, but this is generally well regarded and understood that you know, if you look at particle light scattering measurements and you compare it to mass concentration measurements, there's a nonlinear response due to the interference from relative humidity. And so as you move monitors from region to region where there could be very high humidity, you'll get this kind of exponential increase in light scattering, which again, it screams out the need for some in situ calibration for particle measurements. And then to make particles even more complicated, not only does the response depend on relative humidity, but light scattering also depends on the kinds of particles that you're actually sensing. And so it's not like a gas where you could have a calibration cylinder hooked up to it. Particles are actually different in composition, so shape, size, refractive index, or color affects the scattering properties. And so this is some work that we did in order to inform whether or not we could use these low-cost sensors in different cities where we're doing air pollution epidemiology studies. And so we did co-locations at regulatory sites in all of these cities to see whether or not, one, we could calibrate to the reference instruments, kind of like in our previous, in the previous slides. But two, also try and understand things like relative humidity or temperature, difference in seasons across all these different cities, how that regional context might actually affect the calibration models. And you know, if you look at our paper here and you dig into the methods, you know, the calibration models are really rather simple. They're just statistical regression models, but you know, certainly these days, you know, a lot of groups are using machine learning algorithms and whatnot to fit these calibrations. But this is sort of an interesting thing that we found, which emphasizes the importance of regional calibrations. You know, when we looked across the different cities, when we applied our co-location models locally to our city's monitoring network, generally the correlations with regulatory measurements were pretty good. So the R-squares were getting up into the 0.9s. But if we, say, just took our Seattle calibration model, our data from Seattle, and then just trusted that and just said, well, let's just use our Seattle calibrations across, you know, the entire country, you know, we still got decent correlations, 0.7s, 0.8s in that range, but they weren't as good as our regional specific calibrations. And so, again, data quality is kind of a relative concept, but you know, if we're looking for the sort of highest accuracy, highest precision data, we still like to do our regional calibrations and co-locate with regional authorities and develop our calibration models so that they're really specific to the particle compositions that are in that region and for the seasons that exist there. Okay, so we're starting to move along with our work. You know, people are starting to believe that you know, the low-cost sensors aren't completely random number generators. They're actually performing okay. They might be useful. Then there's this other sort of aspect of the snake oil cell, which was, okay, do people really believe that we could deploy these in large numbers, and are these really low cost? And I started making comments that sort of started to disrupt things, which was low-cost sensors are not low cost. And I think some of the previous speakers alluded to some of the challenges that sort of add cost and complexity to these sensor deployments. And so there's the cost of the underlying sensors, but then you need to get them out into the field. And so everything from the tripods to, you know, the special metal bands that the traffic engineers require that you know, have to put them onto streetlight poles, or, you know, the step ladder that you need to buy, the insurance policies that you need for the cities to allow you to kind of mount these things in case they fall off and hit someone, engineering costs, field maintenance, training, ongoing maintenance. These sensors don't last forever. And so typically they have between a 6-month to a 1-year time frame when we need to kind of take the boxes down and refresh the sensor packages. Networking costs, Many of our studies leverage off of community enthusiasm for having new air pollution monitoring data. And so we have community engagement costs. And then obviously, there's the cost of the research team that are still trying to figure out what is the value of all of this stuff. And I think, Ron alluded to earlier, as researchers, we can get these instruments out there, we can engineer them, we can get them out there, we can collect all the data from them. But we're really just at the very beginning of really demonstrating the value of these low-cost sensors that are actually pretty high cost. So, so I wanted to kind of dig into this one case study, which will hopefully show a little bit of the value from a public health standpoint. So this is a community engaged project which is funded by the National Institutes of Health. This project is now concluded, but it's still being sustained. It involves the California Environmental Health Tracking Program, as well as a community-based organization, Comité Civico del Valle. It's based in the Imperial Valley, which is in Southern California. It's a border community, so it's right at the border of California and Mexico. There's about just under 200,000 people who live in this county. And then across the border is Mexicali, which is like 3 or 4 times the population. So Mexicali is a pretty big city compared to Imperial, which is mainly agricultural, small towns. Why did we set up a monitoring network in Imperial? It turns out that this community has some of the highest asthma rates in all of California. They're also having some really bad issues with COVID right now. And it may have something to do with the comorbidity with asthma. They're not like any other, they're no different from any other community in California. They don't have that many regulatory monitors, and I would say, here they've got 5 in yellow. These are government sites where they do air quality monitoring. This is actually a lot for many counties in California. But the main thing is they're out of attainment for PM10 standards. And again, that may be a contributing factor to some of their asthma problems. So we designed a network through a series of community engagement exercises. And so generally with our community engagement, we trust our local community partners to tell us where the most important places are to establish monitoring. They know their community much more than some academics up in Seattle, 2 states away. So we trust them. And there's about 40 nodes that we set up in this monitoring network. There's co-locations that are built into this as well with the government monitoring. And many of the sites were established at schools because of the asthma problem. They actually operate an asthma flag program. And so there was an opportunity here right off the bat to utilize the data from the more intensive Ivan community air monitoring network that we set up to inform their asthma flag program. So when levels reach a certain threshold, this green flag will switch over to a red flag, and that'll inform the kids at that school who have asthma that they shouldn't be outside doing vigorous activities. The other thing that we've done is, we've done some spatial statistical modeling, and so we set fit surfaces using some geostatistical algorithms to the model, to the monitoring data, and so that we can sort of interpolate and infer what concentrations might be at places where we don't have monitoring. And we've done that both for PM 2.5 and PM course, and we're actually using some surfaces like this for an asthma cohort study that's ongoing right now, where we're recruiting some kids at different schools within the valley. The other interesting thing about this being a border community with Mexico is there's always this question of, who's responsible for sourcing the air pollution? Is U.S. air pollution polluting Mexico, or is Mexico air pollution polluting the U.S.? And so we've run some high split back trajectories, looking at high pollution air events that we've noticed with our monitoring network. And, as you can imagine, the answer is, well, both. And so depending on the direction of the winds and the seasons, sometimes they'll blow one way across the border and sometimes they'll blow the other way across the border. This was an interesting analysis to show the value of community air monitoring. Simple question, we just wanted to identify, how many episodes, high air pollution episodes we observe within a 1-year period. And so this is the government monitoring network, the time series for 6 different sites, and you can see, their data isn't complete, so there's some failures in some of their time series. But I've circled one of the episodes where you see over a short duration of time, some of the levels get really high. So that's an example of an air pollution episode. And so we would count them across the period of a year. And we would do the same thing for our community air monitoring network. And the results from this very sophisticated method of counting is basically we end up with about 10 times as many monitors, about 10 times as many air pollution episodes recognized. But what's really interesting is what that means in terms of reliance and reliability and redundancy in terms of the information over the network. And so if you look at when we identify an air pollution episode from the government monitoring network, 90% of the time when we pick up an episode with that network, we only observe it with a single government monitor. And that's because of the sparsity of the nodes. But when we observe an air pollution episode with our community air monitoring, 68% of the time, the majority of the time, we actually confirm it and we observe it with 5 sites. And so there's some inbuilt redundancy in having a very sort of highly dense monitoring network, at least with PM 2.5. Okay, I'll skip through that. I wanted to mention really briefly, there was crowdsourcing in my title of my slide, and I wanted to move away from some of our stationary monitoring to talk a little bit about personal monitoring, because this is really the holy grail in terms of understanding people's exposures in relationship to their health. And so we've shrunken down our tripod-based box into a little battery-operated personal box, which still has the low-cost particle sensor in it, but it also has accelerometry, GPS, and a data logger. And it's about the size of a deck of cards. And we also collect the particles so that we could do chemical analysis of it afterwards. But someone asked about wildfires earlier. When we did some deployments, we just happened to have our system deployed with study participants during the BC wildfire event. And so you could see that people individually were exposed, and that they were just as exposed individually as the outdoor concentrations indicated, which was really rather depressing because I would have thought that people would move indoors, protect themselves in some way, some fashion, run air cleaners and whatnot. But really personal exposures mirrored outdoor exposures quite well across this week. And if you look at these concentrations, these are sort of Beijing levels of air pollution that are occurring in Seattle. And we're paused right now because of the COVID situation, but already we've got about 3 gigabytes worth of personal exposure monitoring data. And this is a jittered sample within the Seattle area, but we're really excited about this, and we're hoping that this could be a really interesting resource for others that might be interested in doing some data science and data exploration into what personal exposures look like. This is 2 weeks of monitoring for everyone in our cohort, and we have some health measures that are paired with this data as well. So I invite you, if you're interested in this, feel free to reach out to me and pose some research questions. So with that, thanks. There's obviously, these are many different projects, different places, and so we have a lot of different collaborators. Be happy to answer some questions.
Thanks, Edmund. Great talk. I think I'm going to take advantage of the microphone that I have and ask the first question. Given that UW is a neighbor of Microsoft, and what you've seen and know already about what Microsoft is doing in this space from Gavin and Miriam today, and I'm sure you're familiar with Scott and some of the other work happening, is there anything that you think Microsoft should or could be doing differently to help promote this agenda that you're sharing with us today?
Yeah, I think the previous speakers alluded to this, that, there's some challenges as an academic researcher in developing these systems. Developing 40 monitors, or like in our personal monitoring case, we've got about 100 monitors. Those kind of exercises literally kill us, because how do we do that? We have a factory floor of undergraduate students building monitors, which is not what we should be doing. And so it's okay that we do that for research, but eventually we need the commercial sector, even sort of the Microsoft research commercial sector, kind of come in and take this to the next level. And so really it's that scaling, it's bringing the price points down from $6,000 all the way down to, what is it, $200 for some of these technologies to really kind of become pervasive.
Great. Well, I hope Gavin was listening and that he has an opportunity to respond to the gauntlet you just threw down at our feet. So thank you again very much, Edmund, for your talk. Very interesting. We'll now be moving on to our last speaker of the morning. That's John Fink from Portland State University. John will be talking to us about using campuses in the Cascadia corridor to advance smart city innovation. John, the microphone is yours.
Great, thanks. Thank you very much, Scott, for inviting me to participate in this. It's been a great series of talks. I'm going to be talking about some on-the-ground experience that is connected to a number of the things that we've heard about, and be talking about a project that was set up jointly by Portland State University and the city of Portland a couple of years ago to use campuses to test smart city innovation before these innovations are deployed more broadly in the city. And I also want to mention, just in my signature slide here, part of the work that I'm going to be talking about is a collaboration between University of Washington and University of British Columbia, which was actually started by Microsoft about 4 years ago as an attempt to better connect the Cascadia corridor of Seattle, Vancouver, and Portland. And so I'll be talking about that at the end. So under the heading of smart cities, there's 3 challenges that we set out to address. And these are that there's lots and lots of technology that's been proposed for helping cities manage themselves. And the questions are, how do the cities themselves decide which of the many, many options to choose? Second, how does the public assess which ones of those options they think are a good idea and which ones they have concerns about? And the third is, how do companies align their products to the needs of the cities and the desires of the public? So in all 3 of these cases, one of the things that would help is if the technologies could be tested before they're fully deployed. And we heard many examples, Charlie's work with Array of Things and Edmund's work with air quality and Ron as well, that there are lots of opportunities to try things out in cities, but there are also some risks involved in just putting things in neighborhoods before they've been fully vetted. And so we're trying to use campuses as a place to evaluate some of these technologies initially. And one of the main ideas of our initiative is to have a network of campuses where we can be trying similar things in different settings. So this shows 3 of the campuses that we're working with. The one on the left is Portland State University in downtown Portland, and it's completely immersed with the city. When you're on the campus, you can't really tell when you're in the city and out of the city. The upper right is the Oregon Museum of Science and Industry, just across the river, the Willamette River from Portland State. This is smaller, it's 18 acres. The reason it's included is that there's a science museum, but as you can see in the image, there's also parking lots. So there's 11 acres of parking lots, and those parking lots are slated to be turned into a large mixed-use development, commercial and residential, over the next 10 years. And that development is quite open to including technology. And so that's somewhat of a greenfield opportunity. And then the third campus in the lower right is the University of British Columbia, which is much larger than the other two. It's 990 acres. It's a self-contained city. If you look in the back of the slide, you can see the city of Vancouver about 10 miles away from the UBC campus. And what's great about UBC is that because they control virtually all the urban systems themselves, they can try a lot of different things out without impacting other parts of the community. So at the moment, we have these three campuses on the left: Portland State, the Oregon Museum of Science and Industry, University of British Columbia. Those are the first three. This year, we've added the University of Washington Seattle campus and Portland Airport. And we're in discussions about possibly adding Microsoft's Redmond campus, Oregon Health and Science University, and the Oregon Zoo in the future. All of these, what these have in common is each campus has a single owner and more or less a single purpose, and they have more control over what goes on than is the case in the city at large. The ultimate goal is to figure out solutions for cities as a whole, but we're looking at intermediate steps to get there. One of the advantages of having a network of campuses is that we can be opportunistic. And I'll give an example of one deployment that we were prepared to do in Portland at the Portland State campus, monitoring traffic on one of the main streets. But at the last minute, the city of Portland Bureau of Transportation decided they no longer were going to let us use their light poles to deploy the instruments. So because we had a relationship with the University of British Columbia, we took the 4 instruments that we had purchased for Portland and shipped them up to UBC, where they are being part of a network up there. So the rationale behind our Digital City Testbed Center, a couple of things. One is to test before deployment, before full deployment. We really want to be sure that we're partnering with cities. So this is not a series of academic exercises or a number of startups that just say, hey, we have this cool thing, just use it and see what happens. We want to find what the priorities are for the cities and then try to help them achieve those. We have a mix of types of campuses, so academic campuses, corporate campuses, nonprofit campuses like the Science Museum. And we're focused geographically on this Cascadia region of Oregon, Washington, and British Columbia, in part because it's quite homogeneous. There's a lot of similarities among Portland, Seattle, and Vancouver, but enough differences to make it interesting. And then some of the underlying issues that we're trying to deal with through our deployments are replicability, interoperability of different systems that were created by different vendors, and also questions around data sovereignty. So who gets to keep the data that we're all generating through our phones and our devices? These are some of the underlying questions that we're looking at. We have 3 main areas of focus in this initiative today. One is accessibility. So how can urban technology help people with disabilities better negotiate their way around cities? The second is something we're calling smart trees, which is taking the sensor and cloud computing resources that are normally aimed at physical infrastructure in cities like streets and buildings, and how can we use those to monitor the urban tree canopy because of the importance that that canopy has on the urban heat island and air quality and sound reduction and other things like that. And then the third area of focus, which is most of what I'll talk about today, is campus corridors. So setting up locations on campuses where multiple technologies are being deployed to look for synergies that might come up across them. We have a number of partners that we're working with, both through our own initiative and through the City of Portland. And so these are some of the larger corporate partners that we have for specific projects. But equally important and in some ways more exciting, we have a lot of startups that we're working with. And I will say that the set of startups that we have, there's nothing magical about this set. They cover a range of applications. For each one that you could look at, there would probably be another dozen or so alternatives that one could bring in. A few of them are unique, but most of them are in spaces where there are a lot of companies trying things out. And part of what we're interested in is just to have a range of applications developed bottom up by these startups rather than all coming from one vendor like Google and Sidewalk Labs saying, we're going to provide all the solutions. We think that the individual companies have their own ability to right size and perfect what they're doing, and then we're trying to put some of those together in novel ways. And as I mentioned, part of what we're doing is to try to co-locate a number of these applications in particular areas. So this is a map of the Portland State campus, and these are some of the applications that we're trying to co-locate. So issues about questions of how people can get around who use wheelchairs, people who can't see particularly well, looking at questions of bicycle and car collisions, indoor-outdoor air quality, measurements of building occupancy and linking that to HVAC systems. Also, how do we educate the public and get feedback from the public about all these deployments, which relates to one of the questions that came up a couple of talks ago. And so for each of these applications, we have one or more companies whose products we're trying to use, or have the array of things here, so that's not a product, but it's a program. And we're, again, trying to co-locate them. Part of the reason to put them together is for educating the public. So if we just had these things scattered all over the city, you'd miss out on the opportunity of where you could have signage and other interactive means of letting the public know, here's an array of things that we're trying to do in this location, and we'll tell you about them here, and you can ask your questions. So another example of co-location on a campus is back at the University of British Columbia. And the red lines you see there are two of the main streets on the UBC campus, where one of UBC's initiatives called the Aurora Connected Vehicle Testbed is located. And here's a map of those streets, and the circles are intersections where a whole set of instruments are deployed. And part of the goal is to have common instruments deployed on multiple sites so that you can both track vehicles as they move from one location to another, or see how traffic varies from place to place, but also to try out multiple types of sensors and types of applications in the same locations. Now, one of the exciting things about the UBC campus is about a year ago, Rogers Communications, which is one of the largest cell phone providers in Canada, deployed a 5G pilot on campus, and they invested quite a bit of money both in the infrastructure and in the research that goes with it. And so because UBC is part of our network, we're being able to take advantage of that new development. So the Aurora intersection has a whole series of sensors that are deployed on light poles and on traffic signals. And there's a whole range of intelligent transportation system applications that are being developed there. We're coming in rather late to this project. The project's been going on for 4 or 5 years, and we're bringing some additional applications. So this is a list of 9 of the companies whose products we're all deploying on the UBC campus at the Aurora testbed. And I'll show a few examples of these in the next several slides. But as you can get a sense from this slide, there's quite a range of different types of applications. So let me run through 5 of these. So one of these companies is Numina, which is based in Brooklyn, and they have video monitoring of traffic. Like some of the other applications we've heard about in the last 2 days, all of the computing is done on the edge at the instrument. So there is no identifiable information that comes out of the Numina package. All you get are these tracks, and the different colors represent different types of objects. So cars can be distinguished from trucks, buses, bicycles, people in wheelchairs, and scooters. And so this is useful. The application we were interested in was near collisions of bicycles with vehicles. We have, in most cities, excellent data when somebody on a bicycle gets hit by a vehicle because that's reported to the police, but we have very little data on near misses. And so if we had a case where there were 5 hits in a year, we'd like to know, is that 5 out of 10 near misses or 5 out of 1,000? This is a way to start to get a handle on that question. Second application is from out of the University of Washington. This is a program called Access Map. And what Access Map does is to go in and use crowdsourced information to map out the characteristics of sidewalks. So both the whether there are cracks and how smooth they are, also where are their curb cuts and how steep they are. And so on the map on the left, if you can see, the colors correspond to slope. And this is actually in downtown Seattle. So green indicates that these are relatively gentle slopes, and red, like on the right, are very steep. So the idea here is that a person in a wheelchair who knows that they can handle a slope of up to 3 degrees can program that into the app, and it'll give them a route to get from point A to point B. That route will not be the shortest distance, but it will be one that they can handle given the constraints of their mobility. It also includes cases where you can go into a high-rise building on one side, ride an elevator up 1 floor or 2 floors, and then get out on the other side and be higher up. So this is a very neat application. It's also been deployed on the campus of the University of Washington and a number of other locations in the state of Washington. But part of our goal with our network is to take a tool like this and deploy it in multiple sites to see how it can be used with other applications and also how it can work in a variety of settings. So I mentioned that accessibility is one of our main areas of focus, and we're working with several companies that have developed tools like AccessMap, but ones that are particularly designed to help people with visual impairment. And these range from something called Smart Paint, developed by a company in Ohio called Intelligent Material. The way Smart Paint works is there is a rare earth oxide mixed into the paint. And there's a sensor that only picks up that, only detects that rare earth oxide. So there's nothing else in the environment that it reacts to. That sensor is put on the end of a white cane that blind people use, and then the paint is used to mark crosswalks and obstructions. So a person using a cane as they move along, if they hit, if they're outside of the zone they're supposed to be in, their cane will vibrate. So this is one kind of tactile approach, but then there are other systems that use audio to let people know through earpieces where they are in very high resolution. And there's a lot of these kinds of systems that are being developed, and we're trying out several of them on the campuses in our network. I mentioned before that the Portland Airport is one of our campuses, and the main reason they're involved is because they've been a leader in trying out these applications for accessibility. Another application that we're doing turns out to be relevant to COVID, which was not our intent, but the basic idea here, and this is from a company called Sensible Building Science, is that Wi-Fi systems from Cisco calculate how many people are around each of their sensor, or each of their devices. So a router can tell there are 12 people in this room and 50 people in that room. And what Sensible Building Science does is to link that occupancy data to the HVAC systems and the lighting systems to automatically adjust the airflow and the lighting to be where people are, and then to turn it off or turn it down when there are fewer or no people in the space. And this turns out to be a way to save considerable money and energy and carbon emissions by right-sizing the use of HVAC. This was developed at the University of British Columbia as a doctoral thesis a number of years ago. The graduate student who did that is now the head of the company. But UBC was willing to try this out across their very large campus. And what they found was that the savings per building could range anywhere from 5% for a pretty energy efficient building to maybe 20, I think 22% was the highest on some of the older buildings that are not as tight and as well controlled. So now it turns out that this has an additional application which we came up with at Portland State. So over the last year, we've been planning to deploy this at Portland State as an illustration of demand side management and how companies that want to work with utilities to reduce their utility use during times of high energy demand could do it. So we thought, well, we could demonstrate this on the UBC campus. But what we realized in February when COVID started was that if we're going to go back to campus, we're going to want to have particularly high airflow in any of the spaces where people are, particularly if there's going to be classes. Well, having very high airflow turns out to be not very efficient and very expensive. And so even though we want to have high airflow for health reasons, we want to be able to limit it where we can, where there aren't people. And so we proposed to Cisco that we develop this particular application. And we had originally applied for a grant for $30,000 to upgrade the licensing on our Cisco systems in Portland State. And we were having a hard time getting that $30,000. Once we came up with this COVID application, Cisco said, well, we'll just give you a $400,000 grant to upgrade all of the routers on your campus and the licensing there. So this is another exciting example that really was unexpected, that where we could be opportunistic because we were working with this startup that had some other potential applications. The last example I want to give is a company out of London called Hello Lamppost. And what Hello Lamppost does is it allows people to communicate by text message with objects in the urban environment. So it could be a garbage can, like in the center image here, or a manhole cover, or a lamppost, or a statue. And there's a text message, there's a phone number provided, or also a QR code that lets people send a text message to these objects. The objects then respond. And the original idea was just to allow people to have a playful interaction with their urban environment. But it turns out that there are two other benefits that come from this kind of goofy application. One is that in the dialogue that is set up by Hello Lamppost, so for the example of the garbage can, if you say, hello, garbage can, it might respond and say, hello, how are you doing today? Where did you come from today? Or how far away did you come from today? And the last three people who talked to me said that there was a guy playing Frisbee with his dog right nearby. Is that still there? So you can have some questions that collect some environmental information. All of that information is collated and then provided back to whoever it is as the sponsor, in this case, the city. But you can design those questions and answers to ask questions that you want to know what the public's opinions are. So if you could say, for instance, did you know that here on the campus of University of British Columbia, there's a sensor on the lamppost that is monitoring traffic? Do you have any concerns about that? Or conversely, you could just let them know about the nature of these applications. And so this becomes a way to have dialogue, much in the way that you could do with a traditional interview or questionnaire. But people don't really enjoy filling out questionnaires, and people do, in many cases, like having this kind of oddball interaction with these street objects. So the new application of Hello Lamppost is not just to have playful interaction, but to collect and give information back to the public and to the sponsor. So now these are all cases I've been talking about on a particular campus. But what is really important is how we go from campus scale to the city scale, or to the metro scale, or even to a regional scale. And so I want to talk about that for the last few minutes here. So I'm going to start with a slide of downtown, nice aerial image of downtown Portland. And any of you who are thinking about Portland these days, you're not really thinking about smart cities. You're thinking about the federal invasion that we've had over the last 2 weeks. For those of you who haven't been monitoring the news, I just saw 20 minutes ago that the Trump administration has said they're withdrawing all those agents from Portland tomorrow, which is great news for those of us who live here. Anyway, but the reason I'm showing this slide is not for that. It's more to talk about scaling up from campuses. So here's the campus of Portland State University on the south end, southwest corner of downtown. Over here is the Oregon Museum of Science and Industry. And what I want to talk about now is the area just north of the museum. This is called the Central East Side Industrial Preserve. And it's a much larger area, 600 acres, that has been zoned to prevent gentrification. Portland has a long history of manufacturing, and manufacturing, much of which has been located near downtown. Now, this has become cleaner in the last couple of decades, but there's still quite a bit of light manufacturing that goes on. in an area like the Central East Side, or specifically the Central East Side. Part of what we're looking at right now is how to take some of the applications from the OMSI campus and to scale them up to the Central East Side. Central East Side is much more representative of the city as a whole. There's 100 different buildings with maybe 70 different owners, all kinds of different applications. But we're looking at some of these smart city applications we're applying on other campuses and saying, could we deploy some of these in this much more heterogeneous but much more realistic setting and get some benefits that we could calculate going forward? And this is there's examples of this in virtually every city. So if we look at in New York, a group of us from Portland went to New York City right before COVID broke out. We went to the Brooklyn Navy Yard, which is 300 acres, similar to the Central East Side, in that there are many different companies there doing many different things, but there's kind of a common theme to the whole location. And then back in the Pacific Northwest, the Bellevue Spring District in Bellevue, Washington, has some similar attributes. This is right next to the Global Innovation Exchange, which is a joint project of Microsoft and University of Washington and Tsinghua University. So figuring out how to go from an individual campus to these more heterogeneous locations is the next step. But then we also can think about, if we have applications in Portland and Seattle and Vancouver, how can we learn from those? And how can we start to knit together this entire region? The Cascadia region has a number of common themes. It's somewhat homogeneous in terms of attitudes. It's quite green, both politically and physically, with a lot of trees in all the metros. It's a fairly socially aware, progressive political area, quite tech savvy, with a number of tech companies being based here. My background is geology, so I would also point out that in these three images, you can see an active volcano in the background, which is another nice attribute of the area. So having these deployments spread across Cascadia adds another element where we can say, how can we scale up from campus to these much larger scales? So in summary, what I'm trying to describe here is the opportunity to use campuses to try out smart city applications before they're deployed in a larger part of the city or in a metro or in an entire region. We're also co-locating technologies in order to look for new synergies. We also want to be a place, I should have said this earlier, but because campuses are more controlled than cities as a whole, these are places where we can start to assess some of the positive and negative aspects of putting technology in cities. So some of the questions that came up earlier about privacy and data security, these can be addressed in a more controlled way on campuses before you're looking at the city as a whole. So I'll leave it at that and happy to answer any questions.
Thanks very much, John. We have a question from Kristen Lauder. The question is, when thinking about scaling up services that could be deployed to hundreds of cities, how do you envision the science and AI capabilities can and will be brought to bear to understand the data, for example, air quality data, and help cities to make policy decisions?
Great question, a really important one in terms of what I was trying to lay out. I would say one of the things that's important is to work on multiple sites, and trying some of these things out in 2 places is really, really valuable. I mean, Charlie is trying things out across hundreds of sensors in multiple cities, and some of the other initiatives are doing something similar. That's really important, but you can work the bugs out in just doing some things in 2 or 3 locations. So I would say, in terms of specifically how to incorporate AI and some of the machine learning applications we've heard about, take some of the things that are becoming more bulletproof in one location and just see what problems come up when you try to do it in 2 or 3, and then think about what would be the issues if you wanted to go to 5, 10, or 20. I would also say, in the case that you mentioned of, say, 100 cities around the US, take advantage of existing networks, like the Urban Sustainability Directors Network, which is a group that's been around for a decade, involves representatives from virtually all the large cities in the United States. Partner with them because they know who the right people are that can try these things out, rather than have the academics or the corporate people try to figure that out on their own.
Great. And it looks like we've got One more question from Alex Cabral. Alex asks, what challenges do you face or anticipate when scaling up from campuses to cities, particularly when considering that many city neighborhoods have different demographics than college campuses?
That's a really good point as well. And the Portland State campus is not particularly representative of Portland as a whole. And so part of what we're trying to do is to have dialogues with some of these neighborhoods that are not where our campuses are. We're also thinking about expanding to some campuses. So in case of Portland, Portland Community College has some campuses in much more diverse neighborhoods than where Portland State or the Oregon Museum of Science and Industry are. But a lot of what is necessary is to either bring some of these people to where the technologies are, or bring some of the technologies out to the neighborhoods and do some deployments where we can get their feedback, because we definitely don't want to be doing this as an ivory tower exercise.
Super. And a few more questions rolling in here. We'll take advantage of the last 2 minutes with you. Scott Counts asks, where is the best place to go for write-ups on all the technologies you were testing out?
You can drop me an email. I have a paper that's in press from IEEE that talks about a number of these applications. We also have a website. And Scott, we would particularly like to be continuing the dialogue with you and your group because we think the synergies could be really great.
And our last question comes from Wendy Chisholm, also from Microsoft's accessibility team. She asks, great to see applications that benefit people with disabilities. Thank you for being inclusive. When you look at scaling between cities and specifically the access map work, how are you stitching together that work between cities?
But again, by having contacts, local contacts who know those cities well and who might be connected to the groups in those cities who are advocates, say, for people with disabilities. We're also working with national groups like the American Printing House for the Blind, which has an excellent network across the country. Excuse me. We're also working with AARP, which has a presence in most large cities. We actually, in this area, this application, we're particularly excited about what the tech companies have been doing in terms of their accessibility efforts. And I'm not trying to blow smoke here, but Microsoft really has been the leader in terms of AI for accessibility. And so we have come up to Redmond and talked with some of the people a year ago, but we would love to be able to deploy some of the other Microsoft applications in our campus network and to partner on making sure that those applications get more widely deployed.
Great. Wendy included a follow-up question that I'll let you respond to offline since we're out of time now. And there are 1 or 2 other questions that I hope you'll be able to get to as well, John. And thank you very much for the very interesting talk. And thanks to all of our speakers for the great talks we had this morning. Janus has dropped some guidance into the chat window about how the rest of the day should play out, very similar to yesterday. Everyone should take 30 minutes to find some nourishment, take whatever bio breaks you might need to take for a little bit, and then come back to your breakout groups and continue making progress with the breakout groups towards those draft white papers. Thanks, everyone. Enjoy your lunch. We'll see you in 30 minutes, and then we'll all reconvene together for a brief report back at the end of the day at 1:30 Pacific time, and we'll see you then.